Hi, this is the video for the module 11, intro to hypothesis testing. All right, in this video, I'm going to focus mainly on what is the structure or what is the procedure we need to follow to make an hypothesis test. Essentially, is going to be about that. So first, so far, we have seen, for example, about the mean. About the mean, we have seen the parameter, population. The mean is identified by mu. And we have seen the statistic from the sample. And that is denoted by x bar or lowercase x bar. So the point of an hypothesis test is going to be to test whether the difference between what is the hypothetical value for the parameter of the population, whether that value is very different from the value what we observed from the mean. Is the value observed from the mean very different respect to the hypothetical value essentially any hypothesis test is about that. I mean, of course, I'm using here the mean, but this is only one feature of a population or one parameter for which we can be interested in. But in general, the hypothesis tests that we're going to be seeing along the course, they can be about the mean, proportions, and difference between proportions, difference between means, variance. But here in this video, we're going to focus on proportions. Is that okay? In the next video, I'm going to focus on means. But again, anyway, what I want to explain by now here is that we're trying to test whether what we observe in the sample is very different, and that's what I notice how I put quotation marks, very different respect to the value we observe in the sample. But of course, we don't use this phrase here in statistics. To denote that something is very different, we use is there a statistical is the difference statistical significant? Very different. is the difference statistically significant? So this is from common language. This is the language used in statistical language. So essentially, we are going to be testing here whether the values we observe from the sample are very different, or if the difference is statistically significant from the hypothetical values from the population. Essentially, we are doing that. We're going to do that in this, well, in the upcoming videos, but in this video, we will focus on proportions. Note, in this video, we will focus on proportions. All right, first, I'm going to explain the structure of an hypothesis test. Then after that, we are going to be seeing examples. I will try to explain by now the concepts we're using in the language of hypothesis tests. And after that, of course, we're going to see some examples several examples from the homework on Achieve. And when necessary, I will be pointing out some explanations about those concepts, all right? But in general, structure of an hypothesis test. First, identify and describe the parameter. Next, state the hypothesis. Always in the hypothesis test, we're going to be seeing here in this video and in the upcoming videos, we're going to have two hypotheses. The first one, and we can say the main hypothesis, is H null or H0. H null and H0. The other one is the alternative, denoted by HA. H null, H0. State the level of significance. That number is going to be alpha, the value of alpha. This value of alpha in real life, usually, well, in many papers from research, you will realize that the most common values are going to be point, zero point 0.01 or zero point 0.05, or well, in percentage, 1% or 5%. Here, this value here in these exercises, here in college, in this class, usually is going to be given by the problem. Is going to be given. If it is not given, I recommend to use the most common value, that is 0.05 or 5%. Next, test statistic. We will have to compute this. This depends on the parameter. Test statistic. Next, p-value. How to compute the p-value? Well, that is going to depend on p-value. The p-value is going to be the number that we're going to be using here to whether decide if we reject the null hypothesis or not. How do we compute this? Well, this is going to depend on how the alternative is. I will be explaining this with the upcoming exercises. That okay? In the exercises that we're going to be seeing here. P-value. Then after you have the p-value, the rule is if p-value is less than alpha, reject H0. And this is the rule for all the hypothesis tests we're going to be seeing here. If the p-value is less than alpha, we reject the null hypothesis, this one here. The decision of us to whether we have to reject or not is going to be always about the null hypothesis. How do we know whether we have to reject the null hypothesis or not? Again, if the p-value is less than alpha, the level of significance, we reject H0. Otherwise, we don't reject. And then we write down the conclusion. All right. Again, I know there are many things that I haven't explained. I just wanted to understand the general structure, trying to understand completely hypothesis test. I mean, all the details at the beginning, I think can be difficult. I mean, it's not very simple. Anyway, if you do this process in a mechanical way, it's not very complicated. You're going to see it's simple. Trying to understand what is happening, everything what is happening at the beginning, the first time, is not very simple. But again, I'm going to be making notes, pointing out things, all right, as we are seeing more examples and exercises. But by now, I think I want you to remember the structure for, and this is not only for the hypothesis testing or test that we're going to be seeing here for the proportion. No, this structure we can say is the same for any hypothesis test we are going to perform in this course. Identify and describe the parameter. State the hypothesis. Again, always we have two hypotheses, H null, H alternative. State the level of significance, that is the value of alpha. We need something to make our decision, the test statistic. we need to compute the p-value. I will explain later with example what the p-value is and how to compute it, of course. And then after we have computed this, if the p-value is less than this alpha, the level of significance, reject H0. Otherwise, do not reject. And after that, we can write down our conclusion. That is the structure in general. That okay? All right. Let's see some exercises about this. All right, this example from Achieve, it says classify graphs. It says the shaded regions in each of the following standard normal curves represent the significant levels for a left tail, two tail, and right tail. Left tail, two tail, and right tail. Use software or a table of C-critical values, such as this one, to determine the significance level for each graph. All right, here, this graph, notice the shaded area is to the left. Is this one. In this case, we have left tail. How do we know that our hypothesis test is left-tailed? Because the value or the statement in the alternative hypothesis is, in this case, because we're going to be using proportion, is proportion less than something. Proportion less than something. This one is two-tailed. Two-tailed. How do we know we have to use a two-tailed test? It's simple, because in the alternative, we're going to have the proportion different from something. And right tail, this is when the alternative is p greater than something. So in this case, again, I will explain this better when we see the examples. When we're talking about proportions, population proportions, we are going to be using something that we have seen before. Is the values for the C, the standard normal distribution. C is standard normal distribution. That is C representing the values for that random variable. That is a random. Remember that a random variable with standard normal distribution is a random variable that has the mean equal to 0 and the sigma equal to 1. So essentially here we have to find the areas. I mean, we have to find these areas given the standard normal distribution. How do we do that? We can do it with Minitab, as we have seen before, I mean, in previous videos. So go to Minitab. For example, this one. First, this value is negative 2.576. This value, it means that we have to compute the probability that C is less than negative 2.576. We have to compute that essentially. How do we do it? Go to Minitab. Go to Graph, Probability Distribution Plot, View Probability. Okay, again, this is something I have done before in other videos. So this is normal. If it is a standard normal, then the mean is 0 and the standard deviation is 1. And then we have well, notice, is left tail. So we have to use here left tail. And we have a specify x value. The x value is negative 2.576, negative 2.576. And then with that, compute the probability. Okay. 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 Oh, I used the, I'm sorry, I think I did a mistake. So let me do it again. Graph, probability distribution plot, view probability, okay. Mean 0, standard deviation 1, that's okay. But I have to choose left tail. I thought I chose that one, right? Left tail, this one, because it gave me before the right tail, but well. And the value the same, okay, okay. And there you have, you see? So notice the corresponding probability is 0.005, well, rounded up to 3 digits. So the answer is, here you will have to choose 0.005. For this one, we're looking the probability that C is between, no, I'm sorry. We're looking for the probability that C is greater than 1.96 or C is greater than negative 1.96. This is the probability of 1 minus the probability that C is between negative 1.96 and 1.96. So we need to find this probability first and then subtract this from 1. I think Minitab gives you give directly. Let's see. But don't forget the number. It's negative 1.96, 1.96. I mean, when you have a two tail, you're going to have here the same number. But one negative, one positive. So go to Minitab, graph, probability distribution plot, view probability. Okay. Options, here equal tails. Specify x value. You can type the positive or the negative one, I think, no problem. 1.96. And then okay, okay. And there you have, you see? So the answer is, notice I wrote only the positive number, but automatically because I selected the option for two tail. I have the negative 1.96 and the 1.96. So I think it will be the same if you type first the negative number. So in this case, it's 0.025, 0.025. So in this case, since we have twice 0.025, 0.025, 0.025 here and 0.025 from here, if we add this, it's going to be 0.05. And for this one, 1.96 for the last one. For this one, repeat the process. Graph, probability plot, cancel, I'm sorry. Graph, probability distribution plot, view probability, okay. Now use right tail, 1.96, okay, okay, and you will have 0.025. You see that is the value, 0.025. So this is what goes there. There you have. So again, in summary for this, something about this is how do we know? We can essentially we can classify the test as left tail, Q-tail, and right tail. How do we know what is the one we have to use? Is going to depend on how we have set up the alternative. Alternative, we have less than something is left tail. Different to something, Q-tail. Greater than something, right tail. Essentially that. Okay? All right. Now, let's see one example where we have to set up the hypothesis, compute the p-value, and all of that. All right. First, it says a study was designed to determine whether dogs can be trained to identify urine specimens from individuals with bladder cancer. Dogs were first trained to discriminate between urine specimens from patients with bladder cancer and urine specimens from patients with other conditions. After the training was completed, the dogs had to pick one of 7 new urine specimens. So this information is going to be important. Each time, only one of the 7 urine specimens came from a patient with bladder cancer. Out of 54 trials, the dogs identified the correct urine specimen 22 times. If the dogs were simply picking a urine specimen at random, we would expect them to be correct on average 1 out of 7 times. So notice this is saying like the value should be 1 out of 7. Yeah, the value of the proportion should be that. Well, this is what I think. This is what this is trying to say to us. Now, the experiment was designed to test whether dogs can perform better than chance. So essentially, we have dogs trying to detect bladder cancer, and with a sample of 54 trials, they could be able to identify bladder cancer 22 times. But the hypothetical value is supposed to be 1 out of 7 times, 1 divided by 7. So based on this, we have to perform an hypothesis test. All right, first, again, I'm going to follow the steps that I mentioned here. So you can get familiar with the structure. Again, this video is focused on proportions, but the structure is going to be essentially the same for any hypothesis test that we are going to be doing later. All right, so what do we have here? We have first, what is P? P is proportion or true proportion of times dogs can detect bladder cancer. Proportion. P is from proportion. That okay? This is the parameter from the population. Now, first, identify and describe the parameter, the first step. Step number 2, state the hypothesis. Here, the two hypotheses is, again, always, we have two hypotheses. H null, H alternative. H null first is always here. Remember this. H null is always has the parameter, in this case P, the proportion from the population, equal to something. Always is going to be like that. In the null hypothesis, we need to have the parameter, in this case is P, the proportion, equal to something. So, P equal to what? What is supposed to be the hypothetical value? I mean, the true value for the P. Notice, according to this problem, it says we would expect them to be correct on average 1 out of 7 times. That is what is expected, right? I mean, uh, the dogs they can predict not well they would not be actually predicting, but they're going to be right 1 out of 7 times if they do it only by chance. Yeah, maybe the same as we do it. I mean by I mean the people, right? So 1 out of 7 times only by chance. So P is 1 out of 7. Again, null hypothesis, parameter equal to something. In this case, P equal to 1 out of 7. The alternative hypothesis always is going to be the parameter less, greater, or different than that something. How do we know what is the right option we have to choose? I mean, we have to choose greater, less, or different for P. Well, how do we know that? If the problem doesn't say it straight, you have to test this hypothesis against this one. If it doesn't say that, you will have to be able to deduce how the alternative is. Again, once you have set up the null hypothesis, parameter equal to something, the alternative has to be parameter different, less, or greater than something. One of those three. How do we know what is the one? All right. In this case, you will have to pay attention to what the sample says. In this case, the dogs in this sample, they were right 22 times out of 54. 22 times out of 54. This is from the sample. "22 times out of 54 is, notice, is 0.474. And 1 out of 7, the hypothetical value, is only 0.14. So here we see that the value from the sample suggests that dogs can do it better. This suggests that dogs can do it better, right? Better than 1 out of 7. So since this is greater than 1 out of 7, the alternative hypothesis is going to be the proportion is greater than 1 out of 7. Why? Because from the sample suggests that the true proportion is 1 out of 7. That okay? But of course, I mean, this is only an hypothesis. How do we know? Well, we're going to perform a hypothesis test to provide more evidence. But by now, the sample says that it's greater than 1 out of 7. So there you have. Then, level of significance. I think it doesn't say here what is the level of significance, all right? Well, if it doesn't say again, then use alpha equal to 0.05. Level of significance. That okay? I'm following these steps. Identify, state hypothesis, state. Next, test statistic. The test statistic, in this case, for proportions. What do I put for proportions? Because if the test statistics is going to, the way to compute the test statistics is going to change depending on the parameter? Yes. Again, in this video, we are working only with proportions. That's why we're going to be using only one test statistic. But in general, depending on the parameter, maybe the test statistic is going to be different, I mean, as to how to compute it. So in this case, the test statistics is denoted by P observed. No, I'm sorry. is C subscript ups from observe, and it's equal to this, P hat minus P null divided by square root of P null times 1 minus P null divided by n. What is each of these components? P hat, proportion from sample. P hat, proportion from sample. What is this P0 or P null? Is hypothetical value of P in the null hypothesis. So in this case, you can see that the hypothetical value for P is actually 1 out of 7. See that? P null is the hypothetical value for P in the null hypothesis. And of course, what is going to be that? I'm sorry. All right, I'm sorry. So this is P null, the hypothetical value of P in H null. Continuing with this, what is N? N is the size of the sample. Size of the sample, or in this case, number of trials. So here you have P hat, P0. So we have everything what we need. Here, in this exercise, P hat is what? What is the, we have to divide number of successes by the number of trials. In this case, it was 22 times out of 54. So divide 22 times out of 54. We are dealing with proportions, so you should have always a number between 0 and 1, or in percentage between 0 and 100. But if you use it only as a common number, should be a number between 0 and 1, because it is a proportion. So it's going to be 22 out of 54. And we saw this is approximately 0.4074. 0.4074. What is P0 or P null? Is, again, hypothetical value of P in the null hypothesis is 1 out of 7. Then, and N, what is N? How many trials? N, 54 trials, you see? Or the size of the sample. Then, C observed is equal to P hat, in this formula here, this one, P hat 0.4074 minus P null 1 out of 7 divided by the square root of 1 out of 7 times 1 minus 1 out of 7 divided by 54. And you will have to compute this in your calculator, of course. So it's going to be 0.474 minus 1 out of 7. This divided by the square root of 1 out of 7 times 1 minus 1 out of 7 and then this divided by 54. And notice the answer is 5.555. I'm going to round it up to 5.56. 5.56. So C observed is 5.56. There you have the value for C observed. Now we have the value for the test statistic, all right? Identify the parameter, state the hypothesis, the level of significance, test statistic. Then after we have the test statistic, we have to compute the p-value. How do we compute the p-value? All right, the p-value is going to depend, is essentially the area that you will have to compute here. But instead of using these numbers, you will have to use the value of the test statistic. In this case, how do we compute the p-value? You will have to pay attention to the alternative hypothesis. In this case, the alternative hypothesis is p greater. How to compute p-value? If the alternative is p less, then p-value is the probability that C is less than C observed. If the alternative is p greater, p-value is the probability that C is greater than C observed. And if the alternative is p different, the p-value is twice the probability that C is greater than the absolute value of C observed. Absolute value of C observed. So depending on how you have set up the alternative, that is how you need to compute the p-value. In this case, in our problem, notice the p-value is p greater than 1 out of 7. So how do we compute, in this case, the p-value? It falls on this case, is p greater, so the p-value is C that greater than C observed. Here, p-value is equal to the probability that C is greater than C observed. What is the value for C observed? Our statistic is only 5.56. 5.56. There you go. How do we compute this? Well, we have to use we have to go to Minitab and repeat this process. Essentially, we look for this. I mean, it's something that we have done before. Here we have 0, 5.5, 5.56 is here. We're looking for this area. How do we do that? Again, go to I'm sorry. We look for that area here. Is that okay? Remember that C is the standard normal distribution. So we have to look for this area. How do we look for this area? Go to graph, probability distribution plot, view probability, okay, options, is a right tail, right? So choose the right tail. Type the value 5.56, 5.56. Then okay, okay. And notice this is I cannot even see the number. Is 1.3489 raised to the, oh my god, I cannot see it. Well, no problem. In this case, this indicates that the number is very, very close to 0. So I'm going to use the p-value as almost 0. Is that okay? So in this case, the p-value is approximately 0. This symbol means approximately. So now we have the p-value. The p-value is almost 0. Go back to the structure. P-value, what is next? If this rule is the same for any hypothesis test, we're going to be seeing here in this class. If the p-value is less than alpha, reject H null. So since p-value that is almost 0 is less than alpha, that is 0.05, we reject H null. We reject H null, okay? So what is the meaning for this? We have to reject this hypothesis. In other words, we're saying that p equal to 1/7 is not true. What is the one that is supposed to be true? This one, the alternative. If you reject the null hypothesis, you are kind of accepting the alternative, but avoid that word accept. Avoid to use the word except when you're talking about hypothesis tests. We're going to say that the evidence goes in favor of what? Of the alternative. Conclusion. The evidence suggests that the proportion of times dogs detect cancer, well, bladder cancer correctly, is greater than 1 out of 7. And then always, after you have written your conclusion, always state the level of significance at 0.05 or 5% of significance. So, in conclusion, notice the hypothetical value is 1 out of 7, but the value from the sample was 0.474. If the difference between 0.474 respect to 1 out of 7 significant, according to this, yes. The difference between 1 out of 7 population respect to 0.474 sample is very much, or how do we say here, statistically significant. At this level of significance, at 5%. Okay? So this is the structure for any hypothesis test. All right? As we are doing more exercises, I hope you get familiar with this. All right, let's continue with more examples. Oh, I'm sorry. I forgot to complete this. This is for the same exercise. What was the value for C? 5.56. And the p-value is almost 0. And here, how do you respond this in a chip? There is strong evidence that trained dogs identify cancer specimens better than chance would predict. This one. There you go. So let's continue. All right, this exercise. It says, suppose, well, here is not, we have to only complete from several responses. I mean, what would happen? Suppose Ellie is an energy efficiency consultant who is doing research for a hardware store that claims to promote energy efficiency. She wants to determine if the hardware store sells a higher proportion of LED light bulbs than the national average of 10.1%. 10.1%. She uses a computer program to select 60 calendar days from the previous year at random and obtains the store sales records for those days. During those days, the hardware store sold 117 light bulbs and 18 of them were LED. She performs a one sample C-test for a proportion. Using a significance level of 0.05, she calculates a statistic of 1.897, very well, and a p-value of 0.029. Based on her test result, she decides to reject her null hypothesis. That makes sense because 0.029 is less than 0.05, and concludes that there is sufficient evidence to suggest that the amount of LED light bulbs that the hardware store sells is higher than the national average. Determine how changes to each of the following test conditions influence the C statistic, p-value, decision, and conclusion for Alice test. All right, the first one. What about if Ali changes the level of significance to 0.10? In this case, notice, since the p-value is 0.029, Well, first, I mean, you have to choose from here. I'm going to write down the answer, right? And then you can verify that these are answers from this answer bank. First, C statistic. Will not change. P-value will not change, will be the same. What about the decision? If the p-value has to be less than alpha, but now it's 0.10, 0.02 is greater, so decision will change. Decision will change. And conclusion will change, of course. Again, you're supposed to choose these answers from this answer bank, okay? Now, Ali uses a two-tail test instead of a one-tail test and keeps the significance level at 0.05. Here, the same. C-stat won't change. The p-value, since we're modifying the kind of instead of one tail tests, is going to perform two tail tests, so the p-value will increase. Will increase. But the decision will not change. Won't change. And the conclusion will not change. Won't change. Finally, Ali increases her sample to 146. Please verify this. Why this? I mean, I'm going to write down all the answers, right? We have to verify why they're true. But here, the C-stat will increase. Verify why. Will increase. P-value will decrease. I mean, this has to do with the way we have to compute the C-statistic and the p-value. Because notice, the C-statistic depends on the sample size, and the p-value depends on the test statistic. So p-value will decrease. Decision will change. And conclusion will change. All right. All right. Next example. Side effects. An experiment on the side effects of pain relievers assigned patients with arthritis to take one of several over-the-counter pain medications. Of the 440 patients, we have a number, who took one brand of pain reliever, 23 suffered some adverse symptom. If 10% of all patients suffer adverse symptoms, notice this seems to be like the hypothetical value, right? 10% of all patients suffer adverse symptoms. What would be the sampling distribution of the proportion with adverse symptoms in a sample of 440 patients? All right, we have seen before that when we saw the central limit theorem, that the distribution for the proportion is approximately normal. approximately, right? Not exactly normal. Now, how do we set up the hypothesis here? Here is the P, describe the parameter. What is P? Patients who suffer adverse symptoms through proportion of patients with adverse symptoms. And again, as I have mentioned before, how do we set up the hypothesis? We have two, H null and H alternative. H null, always the parameter equal to something. Here it says that 10% of all patients suffer that. So this is supposed to be the hypothetical value, right? So 0.10. So P is supposed to be equal to 0.10. And on the alternative, what do we have to put? P greater, less, or equal, or different. In this case, what does the evidence say? We have 23 out of 440. Is that less or greater than 0.10? 23 divided by 440 is 0.05, so it's less. So the alternative will be less than 0.10. Again, I have described the parameter. There you have. In the null hypothesis, I have to put always the parameter equal to something. What is that something? Has to be the hypothetical value. The hypothetical value, according to this information, is 10% or 0.10 with a percentage. Now, in the alternative, I have to set up the alternative. If it doesn't say, if the exercise doesn't say how I have to do it exactly, then I have to figure this out by myself. How? What does the evidence from the sample say? The evidence from the sample say that 23 out of 440, they suffered this. So what is that? Is approximately 0.05. You see here in the right, 0.05. So that is less than 0.10. That's why I set up P less than 0.10. So I think the option is this one, right? Is this one. Next question, assume the sample is a simple random sample for 3D patients. Are the conditions for inference met? Oh, I haven't talked about that, but yes. You put yes. This is not very relevant for this. So now the test, the statistic, right? How do we compute the test statistic? Set up, describe the parameters, set up the hypothesis. It doesn't say anything as to the level of significance, right? If it doesn't say, then what? Set the level of significance equal to 0.05. Describe the parameters, set up the hypothesis, level of significance. What is next? Test statistic. Test statistic. Is what? C observed equal to P hat minus P null divided by the square root of P null times 1 minus P null divided by N. Here, what is each? P hat is from the sample, 23 out of 440. 23 out of 440. And we saw that is what? That is approximately 0.05, rounded up to 4 digits. 0.0523. 0.0523. 0.0523. What is P null, the hypothetical value from the null hypothesis, P null is 0.10. You see that? 0.10 is 0.10, P null. So 0.10. What is n? The size of the sample is 440. There you have it here. You see? 440. So it's a very big sample. So that means that a lot of, if the sample is random, we have a lot of good information. So here P null equal to 0.10, n equal to 440. Then we have to compute the statistic. That okay? Verify that this is going to be equal to negative 3.337. Verify that. Substitute each of these values here, and you're supposed to have this. The p-value, how do we compute it? Describe the parameter, set up the hypothesis, level of significance, test statistic, next p-value. P-value is equal to what? Is, again, depends on the alternative. The alternative is p less than 0.10. So it's less. So the p-value has to be the probability that C is less than C observed. What is C observed? C less than negative 3.337. And what is that? Again, here you will have to use Minitab to compute this. Go to Minitab, graph, probability distribution plot, view probability, okay. Options is less, so it's a left tail, and type the number here for the observed statistics, negative 3.337, and then okay, and there you have. The value is 0.0004, 3 zeros and 1 4. .0004. There you have. That is the p-value. That okay? So let's continue with this. The C is negative 3.337. Negative 3.337. Correct p-value 0.004. And select the conclusion. Well, I'm going to leave this for you anyway. It's going to be, we have very strong evidence. We have very strong, oh, wait, they're using alpha equal to 0.01, right? But it doesn't say at the beginning. Does it say? No, right? Well, anyway, if the problem is saying, then change that. I'm sorry for that. I didn't see that. So use alpha equal to 0.01 because it is given in the answers, right? Here and here. So yeah, you have to use 0.01. So if the p-value less than 0.01, 0.004, yes, the p-value is less than 0.01. So we write here, since p-value equal to 0.0004 is less than alpha equal to 0.01, we reject H null. So the evidence goes in favor of the alternative that is less than 0.10. So we have to choose the option. We have very strong evidence that fewer, this one here. So this one. The first one. Is that okay? All right. Let's continue. It says range of ankle motion is a contributing factor to falls among the elderly. Suppose a team of researchers studying how combining compression bandages or compression hosiery with different types of footwear affects range of ankle motion. They suspect that less than half of all adults, so notice important information here, less than half wearing compression hosiery and medical shoes will see a decrease in range of ankle motion of at least 2 degrees compared to when they are not wearing compression bandages or compression hosiery and barefoot. They collect sample data from a sample of 29 adults and determine 11 see such a decreasing range of ankle motion. They compute a sample proportion of p hat equal to 0.379. Well, we're lucky here, right? They already compute this for us. Well, it's not. We could have computed that easily, right? The researchers conduct a one sample C test, one sample. So this means it's going to be either p hat, I mean the probability greater, the parameter greater or less. Testing. Oh, we already have here the hypothesis. Notice how the alternative, well, oh, by the way, they use here in the book for the alternative 1. That's okay also, right? In many books, you're going to find with A, H alternative, or H1, but it's exactly the same. P less than 0.5, where P the proportion of the adults to range angle. While wearing compression hosiery with medical shoes, the upper limit of a 95% confidence interval for P is 0.528. Based on this interval, what should the researchers conclude about their C test? All right, I haven't talked about that here. Yeah, so we don't need it by now. So if I haven't talked about that, of course, I cannot evaluate you about that. So by now, we're not using that. How are we going to do this? Well, you have the hypothesis, you have the p hat, so we can compute the test statistic, right? We have to do it here. So the hypothesis again, we have the parameter. What is the parameter here? Parameter P is what? Proportions of adults, proportion of adults wearing compression is this part, okay? But I won't write everything. So wearing compression hosiery and medical shoes will see a decrease. Compression hosiery that see a decrease. In range of ankle. There you have. That is the parameter and the description for the parameter. The hypothesis, we already have them here. P.5 less. The alpha, do we have the alpha here? No, we don't have it. So I think we have to use alpha equal to 0.05. So parameter, hypothesis, alpha, test, statistic. What is the test statistic here? Remember the test statistic? How do we compute that? Is C observed equal to P hat minus P null divided by P null times 1 minus P null divided by N. Here, P hat is 0.379. P null is the hypothetical value of P in the null hypothesis, 0.5. N is 29. And that's all what we need, right? So let's compute that. It's going to be 0.379 minus 0.5. First, I compute this part, P hat minus P0, 0.379 minus 0.5, and divided by this. Answer divided by the square root of 0.5 times 1 minus 0.5 divided by 29, negative 1.303. So C observed is negative 1.30, negative 1.30. So what is the p-value? Then the p-value how do we compute the p-value? Again, depends on the alternative. The alternative is p less, so the p-value is what? Probability that C is less than C observed. Probability that C is less than negative 1.30. And you will have to use Minitab to compute this. So again, go to graph, probability distribution plot, view probability, okay, options, negative 1.30. It is left tail, so be sure you shoot that one, this one, okay, okay. .0968. .0968 p-value. Okay, so if the alpha is 0.05 and the p-value is 0.0968, notice how the p-value is not less than 0.05. So in this case, we do not reject the null hypothesis. So here, what you have to put here in these slots, right, is here is fail to reject at 0.05. Why not? Because in this case, the proportion from the parameter is significantly greater than the sample. You have to choose the option 0.5 less than 0.379. Okay, I mean, those are given answers, all right, that you have to choose from there. I mean, you don't have to type, you cannot type in this question the right answer. I mean, you only have to choose from options here in these slots. So only do this, yeah? All right. Finally, the last example. According to a report published by the Center for Disease Control in 2011, approximately 1 in 2 people with asthma had an asthma attack in 2008. So again, notice, it seems that we are provided right now with important information. 1 in 2 people, so that means 1/2 or 0.50. A recent health survey conducted in 2015 by the National Health Center for Health Statistics collected asthma data for the U.S. adult sample. The file provided contains data on whether or not U.S. adults with asthma living in the Northeast had an asthma attack in the past 12 months. The data file provided contains a variable called asthma attack, which either has a value 1 if an asthma attack has occurred in the past 12 months, or 0 if no asthma attacks occur in the past 12 months. Click to download the data in your preferred format, all right? This data is provided on a chip, but I think we don't need it here. Carry out a hypothesis test with a significance level of 0.01, all right, to determine the proportion of U.S. adults with asthma living in the Northeast that have had an asthma attack in the past 12 months differ from 50%. Use software to compute the p-value to test the null hypothesis. So notice, we already have here the null hypothesis. And here in this case, they're saying that we have to use the alternative, p different. So in this case, we have to compute the p-value another way. So, all right, I'm going to show you how to compute the p-value. But wait. PHAT, you want to find software manual, unless my attack has occurred in the past 2 months or not. All right. So, P proportion of adults living in the Northeast that had an asthma attack. Describe the parameter. There you have. Hypotheses. The hypotheses are already provided. H null, P equal to 0.5, H alternative, P different from 0.5. Level of significance, 0.01 is given there, you see? Level of significance is given here. So we don't have any choice about this. And what do we need to do? Well, we need to compute the test statistic, right? I think I have the file here. So go to Minitab. You will have to download the file and then open it, of course. Open the file, worksheet, local file. I have it here on my computer. It's this one. So how do you know the proportion here? We only need the p-hat. I mean, since 1 means they had or an asthma attack has occurred, then we need to only count the number of ones and divide it by the total. In that case, we can only compute the mean for this, right? So go to calc, well, basic stat, display descriptive for this variable, And we only need the mean here. So the rest, we can skip this or avoid that. Only the mean. Only the mean so that we can count the number of ones divided by the total. So the mean is 0.465. You see that? 0.465. So that is p hat. P hat. Well, first, the test statistic is C observed is equal to p hat minus p null divided by p null times 1 minus p null divided by n. Here, p hat is what? 0.465. 0.465. What is the size of the sample? It doesn't say the size of the sample here, right? Well, how can we compute that? I will let you know. But first, P null is what? Hypothetical value from in H null is 0.5. And the size of the sample here, well, we have to use Minitab. In this case, we need to know only how many value we have here in this column, the column C1. So go to Stat, Basic, Display, Statistic. Here we have a command to count the number of values. So this one, N total. You see? Choose this option, N total, here, this one. And then OK, and then OK, and you're going to have the mean and the total, 856. So we have 856. All right, so what do we do here? The p-value, we have to be, please verify the p-value. I'm going to let you know the p-value. All right, so do we have to complete the rest? Is that okay? You already have these components. Find the C observed, and once you have the C observed, all right, well, in this case we have, oh, no, let me do it. So C observed is what? 0.5 minus, no, 0.465 minus 0.5 divided by 0.5 times 1 minus 0.5 divided by n, that is 856. So we need to compute that in our calculators. 0.465 minus 0.5. That answer divided by the square root of 0.5 times 1 minus 0.5 divided by, what was the value for n? 856. So it's negative 2.04, negative 2.05. You see the number here on the right? I'm sorry, I forgot to show you this screen. I'm sorry. Well, I only did the computations in my calculator. Is that okay? 0.465 minus, to compute it, the p hat, 0.465 minus 0.5, and then answer divided by this, and the answer is, notice, negative 2.05. Negative 2.05. Yeah, I'm sorry for not showing to you this. So, but this is what I was computing here. Negative 2.05, that is the value for the test statistic. You can verify that. negative 2.05. You know, I don't know what happened, but suddenly this stopped. Oh, I'm sorry. The p-value is, the test statistic is negative 2.05. Negative 2.05. So in this case, notice the alternative is different. You see that? So in this case, the p-value has to be computed like this. P-value is equal to, go to Minitab. It's going to be a two-sided test. Graph, probability distribution plot, view probability, okay. Options, here choose the option equal tails because the alternative is different. Type the value we found before is the value for the test statistic is negative 2.05. Type only that, negative 2.05. Okay, and then okay. And you are going to be given this. So in this case, the value for the test statistic, wait a minute, is going to be the sum for these two. For this and for this one, 0.02, 0.02. But wait, let me be sure that I have my computations correct. So we had here 856.465. So it seems to be correct, right? 856.5, 1 minus 0.5, negative 2.5. Negative 2.5. All right, it seems to be correct. So negative 2.05. So the sum of these two, so multiply negative 0.02, multiply this number, or add these two numbers. That is going to be the p-value. 0.02 plus 0.02 is going to be 0.04. So the p-value is going to be 0.02 plus 0.02 equal to 0.04. There you have. There you have. So what do we do? Do we reject or not? Since the p-value is not less, the p-value is not less than the level of significance. Is that okay? The p-value is greater, so we do not reject. Is not less than 0.01, we don't reject. H null. And this is what you have to put here. P-value 0.04, the null hypothesis Do not, here you have to put do not reject. Since the p-value is greater than. According to the answer that I can see from a chip, it seems that my p-value is wrong. Anyway, my two answers are correct. This one and this one. I mean, the decision is going to be correct, but my p-value seems not to be the same. I don't know why. Maybe I'm doing something wrong. But well, anyway, if I let me investigate that. If I find that the p-value is wrong, I will create an announcement to let you know that. Okay. All right. But anyway, the decisions are going to be correct. That's all. If you don't have question, I'm sorry. If you have any question, you please send me an email to let me know, or go to my office hours. That's all by now. See you later.